Hello, my dear. Welcome to IMS GATE Academy. I hope your preparation going to be in the right direction. But my dear, tomorrow, it's your performance of the GATE. Why? Because in the GATE, tomorrow you have a GATE examination of the mechanical engineering. And why we are taking the session at right now? Why? Because here I will discuss about the subject of fluid mechanics, in which we have go through a quick revision so that you can better perform the fluid mechanics in the tomorrow's GATE examination. See, my dear, what is the problem with the fluid mechanics? See, you are study the fluid mechanics thoroughly, no problem. And also, you are very confident in the fluid mechanics that, yes, sir, I solve all the problem. But what is the problem? When you solve the problem, you just stuck at anywhere. So, what is the best method? Just listen and sit at that time, और उसके बाद आप बिल्कुल एकदम कॉन्शियस हो जाइए 3 घंटे के लिए. फॉर 3 hours you have to be very conscious. Okay, you have to very conscious, and automatically we are revise all the concept related to the fluid mechanics, so that you are very comfortable and very confident when you are enter to the GATE examination. Okay, so for that, this is my one of the best favorite question, which is related to the boundary layer, so that we revise the formula. See what is that? GATE, in the GATE we always expected that there is a new question. Yes, it is a new question, but it is not a very tough question like IITs JEE examination. So if you have practice enough for the particular topic, if you have a practice more and more practice for the of the question, previous year question or new question for the particular topic, and how to tackle that and how to implement that concept, you can easily solve that particular question. It is not difficult very much. Okay, so what is that, beta? See, this question is related to the boundary layer, right? This question, 1 second, beta. This question is related to your boundary layer. Okay, boundary layer. Mind it, this is the question which is most expected in it is in either in civil department or a mechanical department. So what is that, beta? One second, what is happening? One second, beta. Yes, yes. Now it is clear. Voice is coming. No problem. Yes, it is clear, beta. Very good, very good. Yes, it is clear. Now it is clear. Okay. So this is your fluid velocity which is incoming to this channel. Okay. Now, what is the property is that when the fluid is entering to this channel, there must be a development of a boundary layer. Very important. There must be a development of a boundary layer. There must be a development of a boundary layer. Okay. There must be a development of a boundary layer. So this development of a boundary layer, the fluid, see, this is like that. That means converging nature. Okay, this is a converging nature. So there must be a accelerating fluid. So if we want that the uniform flow, if you want that there is a uniform flow, so what we do? We do a tiltation. That means we tilt, how much we tilt this solid boundary, how much we tilt this solid boundary theta, how much the tiltation angle theta, you have to calculate it. Please listen very carefully. See, there is a wind tunnel. This question must be expected. Okay, beta, this type of concept. So there is a wind tunnel test in which the fluid is approaching into the wind tunnel due to the property of the viscosity, the development of a boundary layer due to a no slip condition. So there must be a space in which the fluid is flowing. This is generally called core region. So the space which is the fluid is flowing has the velocity will increase, or velocity may be changed, or the acceleration. There is a fluid is accelerating. So if we want that there is a uniform velocity, there must be that we incline this plate, tunnel, to theta angle. Shift, how much we shift this angle theta so that velocity is uniform. Velocity is uniform. So what is that question? Question is asking that, see, very important. What is that? This is 1 meter square. That means this is a square cross section. 1 meter. This is your cross section is a square, and this is your 1 meter, and this is your 1 meter. Okay. So this is 1 meter square cross section. Okay. By 6 meter long, and this is your 6 meter long. How much it is long? This is your 6 meter long. How much it is long? 6 meter long. Okay. This is your 6 meter long. Okay. Now, along with the air moving at an average velocity, that means it will move with an average velocity. This velocity, it is moving with an average velocity 30 meter per second. Okay. Now, to account for the growing boundary layer, that means to account, you consider there is a growth of a boundary layer. This is your growth of a boundary layer. That means this is your boundary layer growth. Boundary layer growth. This is your growth of a boundary layer. So, to account the growth of a boundary layer, the wall are slanted slightly outward. That means to compensate this boundary layer, the wall of the tunnel will slanted outward. How much angle? Theta angle. The wall is slanted outward. How much angle? Theta angle. The wall is slanted outward. How much angle? Theta angle. Okay, no problem. At what angle? That means at what theta? At what theta? At what theta should be the wall will slanted? At what theta the wall will slanted between very important, x is equal to 2 meter to x is equal to 4 meter. 4 meter to keep the velocity is constant. To keep the velocity is constant. Please solve. How to solve? Please solve. To keep the velocity is constant. That means if there is a fluid is flowing through this uniform velocity, there must be a development of a boundary layer. To compensate this, to minimize this boundary layer effect, we slanted the wall outward with angle theta. At section x is equal to 2 to x is equal to 4, we are slanted. So what is the theta angle? For that, we have to achieve a constant velocity. We have to achieve a constant velocity, right? This is the question. And my dear, this type of concept you never seen on your YouTube channel, I am damn sure. Why? Because this question is very R&D question. This gives the extra feel of the fluid mechanics, and this question is very important for the both civil engineering as well as mechanical engineering department. So this type of why? Because beta, why this question is important? Think like that. Why I am telling that this question is important? Why? Because this question is important with respect to the practical application. This will apply practically during the wind tunnel test. And you heard about what is the wind tunnel test. This is the concept of wind tunnel test. Wind tunnel test. Wind tunnel test. So what is the wind tunnel test? You have to also, so this have a multiple concept, and mind it. The first point is clear. The second point, why this question is important? Why? Because this is aptitude type question. It is not lengthy, my dear. In the GATE graduation aptitude test. So this is aptitude type question. It is not a lengthy question like a semester or ES conventional question. No, it is an aptitude type question. So with this respect, with this point of respect, this question is very important. So beta, see very carefully what I am telling. What I am telling. See very carefully. See, this is at x is equal to 2 and this is at x equal to 4. Between x is equal to 2, x equal to 2 to x is equal to 4, we slant the wall will slant at angle theta. So beta, how much the boundary layer thickness? First you calculate. See, very important, I am telling you. This is very important. So at x is equal to 2 and at x is equal to 4, you just calculate the boundary layer thickness. This is the first click. So this is at x is equal to x at delta at 2 meter, and this is your delta at 4 meter. How to calculate the boundary layer thickness? This is your boundary layer thickness. Boundary layer thickness. How to calculate? See, very important. This is the format of the question. This is the format of the question. Now, how to calculate? How to calculate? This is the format of question. So, so now we are bothering about x is equal to 2 to x is equal to 4. X is equal to 2 to x is equal to 4. So this is our wind tunnel, right? This is at x is equal to 2 and this is at x is equal to 4. No problem. Okay. Now we are slanting this and we are slanting this. We are slanting this. No problem at all. We are slanting this so that the velocity is uniform, so that the velocity is constant. We are slanting this. So see, this is not like that. 1 second. 1 second, beta. 1 second. 1 second. This is your wind tunnel. Okay. Right. This is your x is equal to 2 and this is your x is equal to 4 and the wind tunnel is at 6. Okay. So this is your wind tunnel. Now there is due to the fluid flow, there must be a development of a boundary layer. To compensate the boundary layer, the wall shifted outward. The wall shifted outward. Why? Because there must be a development of a boundary layer. There must be a development of a boundary layer. So to compensate the if this will develop the boundary layer, if the development of a boundary layer, see my dear friend, very important, I am telling you, if we compensate this one, okay, one second. So, right. Okay. So, this is our see. So, this is our beta, this is our core region. What is this called? This is called core. This is called core. This is called core. This is called core. Okay. This is called core region. Okay. Now, what is the characteristic of this core region? In this core region, the velocity is continuously increasing. Velocity is continuously increasing. Velocity is continuously increasing. So we cannot judge the accurate result. So what for that we have to tilt outward the wall at angle theta. This is your theta. This angle is theta. You may say that like that. This is your angle theta. How much you tilt? This is angle theta. So if you tilt the theta, so you have to find this theta. So there is a tiltation at this. There is a must displacement of outward at this is delta. So this is your delta at 6 and this is your delta at 2. Delta at 2. So this is your delta at 2. Now this is the now there is a only geometry. So how to find delta 2, and the cross section is rectangular, and rectangular there is a 1 meter cross 1 meter. There is a 1 meter cross 1 meter. Okay, length is 6 meter. Your total length is 6 meter. Velocity which is entering is uniform is 30 meter per second. All of are given. That means this is the cross sectional. Cross section is 1 into 1 meter. Length is 6 meter. And the velocity which is uniform 8 meter per 30 meter per second. 30 meter per second. This is given. 30 meter per second. This is given. Now beta, see what is the approach? See, we take this triangle. Okay, we take this triangle. So what is tan theta? Tan theta. What is the tan theta? This delta, see, what is we can write? Delta displacement thickness at 6 minus displacement thickness at 2 divided by distance. That means 4 minus 2. See the beauty. This is called aptitude. This is called aptitude. Okay. This is called aptitude. So this is your tan theta. Okay. This is called aptitude. 1 second, beta. Okay, so this is your tan theta. Delta is equal to 6 minus delta is equal to 2 is divided by 4 minus 2. Now the next target is how to calculate delta at 6 and how to calculate delta at 2. So this is your first step. What is the second step? What is the second step? Second step is we know that, see, first we check whether the fluid flow is laminar or turbulent, so that we can apply so now definition of displacement. First calculate the Reynolds number. What is the Reynolds number? we know that Reynolds number is UX, REX divided by nu. This is nu. So what is U it is given. So if you calculate at x is equal to 2 meter. So what is the Reynolds number? The U velocity is uniform 30, x is 2 divided by kinematic viscosity, it is given beta 1.5 cross 10 to the power minus 4 minus 5. Okay. So and what is x is equal to 4 meter RE 30 cross 4 divided by 1.5 cross 10 to the power minus 5. So this is your 4 cross 10 to the power 6 and this is your 8 cross 4 cross 10 to the power 6 and this is your 8 cross. See the beauty. Now you tell, sir, what is this? Whether this is laminar or turbulent. Why? Because there is a flat plate. The laminar, it is laminar or turbulent? It is turbulent flow. It is a turbulent flow in between x is equal to 2 to x is equal to 4. Now, this is the second. Now, third step, we know that from the Blasius equation, if the flow is turbulent, what is the boundary layer relation between the boundary layer thickness and the Reynolds number? This is very important. Step third. What is the step third? For turbulent flow. For turbulent flow, what we know that displacement thickness delta divided by x is equal to 0.0478 divided by REX power 1 by 5. Now you say that, sir, this formula, how we can remember? This is not remember. Why? Because in the gate, this formula, empirical relation, it is given. But it is given in two forms. One is the laminar, other is, good evening, Pratik. One is laminar, other is turbulent. Good evening, Atul. So, you just pick up which formula is applicable. For that, you just calculate the Reynolds number. For that, you just calculate the Reynolds number. Why? Why? Because you have information about what is the laminar and what is the turbulent. Okay, no problem. So pick this formula. Okay, now, so put x is equal to 2, find delta, Reynolds number at 2, you have this value. So from this, you have to delta at 2 and delta at 4 meter. So what is the displacement at 2? The displacement at 2, 4.6 cross 10 to the power minus 3 meter, and displacement at 4, 8 cross 10 to the power minus 3 meter. This is the beauty. Now if we have delta, a delta 2 and delta 4, now we can easily put the value in this equation. See the beauty? We can easily put this value in this equation. So delta at 6 is equal to minus delta at 2 divided by 4 minus 2. So what is that? So tan theta is equal to delta at 4, 8 cross 10 to the power minus 3 minus 4.6 cross 10 to the power minus 3 divided by 4 minus 2. From this calculation, from this equation, we can easily find what is the tiltation angle. So this tiltation angle is approximately 0.1 degree. 0.1 degree. This is the question which is asked expected to ask. So what is this condition? In this equation we have to identify two formulas. What is that? Number first is that how to apply boundary layer thickness delta, and other how to judge the flow condition, that means flow pattern, flow information, that means whether it is laminar or turbulent. According to that we can apply the Reynolds number. So my dear, this is very good question. Okay, now the second question, which is very important, this is very important question beta, I know. See, so this is the wind tunnel test, and also we have to next question which is also related to the boundary layer, and this boundary layer and drag, and for that we have to revise the formula. Okay, we have to revise that formula. What is that? Okay, so first select a pen, smaller tip, yellow, larger. Okay, now so what is that beta? See, if there is a flow, what is the drag condition? See, drag and lift, this type of the forces is depends upon the surface geometry. So if we change the surface geometry, these two phenomena will change. Like that, in the GATE examination, it may be that the geometry is little bit tough, so that you can apply the mathematical tool like integration or differentiation. Without directly calculate the surface area, you cannot able to calculate the surface area directly, a surface information directly. You have to calculate by the integration method. So for that field, we can take this question. What is that beta? See, there is a triangular plate, very important, I am telling you. This is a triangular plate. This is very important. Okay. Okay, this is your triangular plate. Okay, now this is your triangular plate. In the triangular plate, see, this is like a triangular plate. You think that this is our triangular plate, and the fluid is flowing. So fluid will contact to this front surface, also the back surface. Okay. Now what is the given coordinate? This is given y-axis. This is your y-axis, and see, this is your y-axis, not total. At this point, see, very important, coordinate is very important beta. See, we take at this point, this is our x-axis, okay, and this is our y-axis. Okay, this is our y-axis, this is our x-axis, this is our coordinate 0, 0. Okay, we'll take, no problem. Okay, now this length it is given, this base it is given. How much it is given? It is given with a 2 meter. It is given 2 meter. Okay, this is not given, no problem. And the fluid which is approaching, over the triangular plate, is 1 meter per second. The fluid which is approaching over the plate is 1 meter per second. Okay, no problem at all. Now, see, the question is, a thin equilateral triangular plate is immersed parallel to a 1 meter stream air. That means this is your air beta, air, at a standard condition, estimate the skin friction on this plate. So what we find? Skin friction drag on this plate. Now again, this question is very important for both branches, either mechanical or civil. So you have to find skin friction drag on the plate. This is given. So how to calculate? This is very important question. There is a plate, it is given, triangular plate, and the fluid is flowing over this front and back also. That means this plate is, see, what is the practical approach? What is the practicality? You see that there is a car is moving, and out in the window you have to draw the hand in your window like that. So the plate, in your hand, the car is moving. That means car is moving, and your hand is outside from the door, window of the car. So there must be flow of air. So this is a triangular shape. So the fluid is approaching here, this surface also contacting and this surface also contacting. So what is the skin friction drag on this plate? What is the skin friction drag on this plate? Mind it, the fluid is flowing from the base to the tip, not tip to the base. It is flowing from the base to the tip. Okay, no problem. See beta, I give you one subtle concept here, which is never found in anywhere, never found in anywhere on the YouTube channel or any book also for that crisp knowledge. So what is that? See, what is that beta? If you find the drag friction coefficient, what is your prime motive to calculate? What is the prime motive to calculate the drag friction? Please tell, please comment that what is the prime motive to calculate this drag? So there are two things beta. One is the pressure drag, other is the friction drag. One is the pressure drag, other is the friction drag. So how to calculate? Let's see how to calculate this friction drag and pressure drag. So what is the key where the many students get confused here? What is that? Just I am giving you 1 second beta. Just I am giving you 1 second. So what is the motive for that? Just I am giving you. See, there are two things here. See, beta, very important, I am telling you. This is just a revision classes so that you can able to get very confident in the tomorrow GATE examination. So what is that? Just wait for the second, while a second, I am just discussing. So there must be a two things. You know what is the friction drag and what is the pressure drag? You know what is the friction drag and what is the pressure drag? You know this thing. So according to this, we have to calculate what is the friction. 1 second. There may be here. What is the friction drag and what is the pressure drag? 1 second. How to calculate the friction drag and pressure drag for any surfaces which is exposed in the air, which is exposed in the air. 1 second. Which is exposed in the air. Okay, I think 1 second beta, 1 second. See, so there are two things. Yes, there are two things. So beta, one subtle concept you always remember. What is that? This is very important. What is that? See here. One is the friction coefficient. Friction coefficient. Other is drag coefficient. There are two terms. Don't confuse with these two terms. One is the friction coefficient, other is the drag coefficient. Thank you, Saurabh. One is the friction coefficient, other is the drag coefficient. So, if the plate which is exposed to the fluid, on that And what is the geometry? I don't know. There is a geometry is triangular, there is a geometry of the plate, rectangular, doesn't matter. But if we have the information about friction coefficient and a drag coefficient, if there is a surface, it is given. This is the surface. It is given, and how to calculate? Yeah, what is the friction coefficient? What is the drag coefficient? How to calculate for that one? Yeah, if the friction coefficient is given and drag coefficient is given, how to calculate? These two things are very important. See, this friction coefficient, we do not CF. We do not CF, and this is denoted by CD. First thing, CF is the friction coefficient and CD is the drag coefficient. See, my dear, this is the friction coefficient, this is the drag coefficient. Okay, now one thing is very important. This is very important, very important. I'm telling why I'm telling as a teacher. Why I'm telling as a teacher? Why? Because 99% students get confused here. This question. What is that? See, friction drag is defined by shear. See, that means is defined by shear. That means what is the shear force? What is the shear stress? That according to that we define the friction coefficient. But how the drag coefficient is defined? See, it is defined by shear. Very important. Shear stresses at any point, that is X. That means if there is a plate and we define the friction coefficient, if you define the friction coefficient, this is defined by shear stress at any point. This is very important, I'm telling you. So that sometime we represent as CFX. Why? Because it is as a local, it is written as a local. It is defined as X is another, if the X is different, so CF is also different. So sometimes this is called local skin friction coefficient. Okay, right. That means if this is your plate, very important, if this is your plate and fluid is approaching here, now if we take at any cross section, first find the shear stress on this cross section. At this cross section, what is tau value? Okay, what is tau value? First find. Right, this is tau at any X. At X, this is tau value at X. Okay, this is the tau value at X. See, this tau will differ. Very important. At the leading edge and at the trailing edge, these are differ. That means if the flow is exposed more and more to the plate, this shear stress will reduce. That means tau at a leading edge divided by tau at a trailing edge is always greater than 1. Why? Because the shear stress, when the fluid is flowing from the leading edge to trailing edge, the shear stress is continuously reducing. Why? It is detailed in the class. Okay, already we detailed in the class. Okay, now, so this is at any point. At any point. Okay, at any point. Now, so at any point we have to find CFX. How to find CFX? So CFX is equal to, we have find from the Blassey equation 0.664 divided by local Reynolds number Rex power 1/2 या root under x. right? So this is your CFX. Okay. Now what is this value? This value also equal to the at any point, that means tau is the local shear stress, tau at any point x divided by dynamic pressure, half rho US square. So this is very important formula. How to find this? So just you think that if you find the friction coefficient, this friction coefficient is defined by shear stress at any point. So we don't bother about the integration. It is at any point. We cannot calculate the total. Okay, now what is the drag coefficient? What is the drag coefficient? Is defined by drag force. Drag force is defined by drag force over. It is defined by drag force over some length of the plate. Some length of the plate or given length of the plate. Given length of the, it is defined by some length of the plate or given length of the, this is very important, I am telling you. See, it is defined by the shear stress at any point, but it is defined over the length, yeah, given length. That means if you find the drag coefficient, you have to find the total length. That means, see, if this is our plate, very important, if this is our plate, beta, okay, this is our plate. So let's suppose this is our length L, length of the plate, and so if you find the total, you just integrate it. Why? Because the area of the plate which is exposed to the fluid will differ. That means will increase. That means in this area the fluid is less, and this area of the fluid is more, and again more, and that means the fluid which is contacting with the plate is increasing continuously. Okay, increasing continuously. So we take a element here, very important. So on this element you have to find the shear stress. On this element you have to find the shear stress. So you have to find tau W. You have to find tau W at dx length. This is your dx at x. Okay, you have to find tau W at x. Now, how to find drag? First, why? Because how to find drag force? Why? It is defined by drag force. Very important. How to find a drag force? That means F D is equal to integration x is equal to 0 to x is equal to L. See, this is force. What is the stress? Stress of force upon area. Stress of force upon area. So what is the force? Stress by area. What is the force? Stress into area. What is the area of this element? Dx into unit width. If we take width is unit. Width is unit. If we take width is unit. So what is that? This Fd is equal to tau at wall into dx into 1. So from this one you have to find the drag force. Now once you find the drag force, this is the total drag force. Now once you find this drag force divided by the pressure, dynamic pressure, half rho US square gives the drag coefficient. This is the beauty of, my dear. That means if you find CD, so this CD is equal to this FD divided by half rho U square. This is very important, I'm telling you. So this is your C. So in the drag coefficient, if you find the drag coefficient, it is not written by local. Why? Because it is an integral form. That means it is a total form. So drag is the total. Drag is the total. And friction coefficient, drag coefficient is the total. And friction coefficient is at a particular, at any cross section. So if you take at any elemental length, you can find, you have a shear stress, you can just integrate it, you can find the drag force half. This is your drag coefficient. Okay. Now this drag coefficient is equal to, from the Blasius equation, 1.3 1.328 divided by total, see the beauty, REL half. This is the very different thing. See, this is your REX, this is your REL. That means Reynolds number at this L. Half 1.32, this is your point. This, so see, this formula it is not given. You have to suppose to remember. This formula it is not given. You have to suppose to remember. And how to find the drag force? This is your drag force. So how to calculate the friction coefficient? How to calculate the drag coefficient? This is very subtle concept is there. This is very subtle concept. You can never found in this crisp manner of any textbook. Okay. Now come to this problem. Come to this problem. Come to this problem. What is that? Just think. So we have to find. We have to find what is that? Skin friction drag on the plate. See, what is the skin friction drag? This is the skin friction drag. This is the skin friction drag also. Skin friction drag also. This is the skin friction drag. Okay. How to find skin friction drag? Now, so this is at any point. Okay. So from this, what is the approach? See, this is given equilateral triangle. This is an equilateral triangle. Equilateral triangle in which theta is equal to 30 degree. 30 degree it is given. This theta. This theta value is 30 degree. This theta value is 30 degree. Okay. This theta value is 30 degree. No problem at all. Now, beta, what is the concept behind this equation, this question? See, if we say that whether during the fluid flowing over the plate, this triangular plate is entirely laminar, entirely turbulent, somewhere it is laminar, then it is turbulent. This type of points you can think in this such type of question. So how to decide that when the fluid is flowing, what is the nature? That means, beta, whether the fluid is flowing over this plate, this is entirely fully developed for the laminar, fully developed for the turbulent. See, laminar then turbulent. See, if we find the x length over which, if we assume there is a laminar, and if you find the length of this length, and if you find this length and if this length, if you calculate, if you suppose that there is a laminar, see very important information, if you suppose that, हम ऐसा मानते, if you suppose that the total, the fluid is totally laminar, if the fluid is totally laminar, then the length, if you calculate the length, that length is the less than the length which is calculated by the laminar. Yes or not? So that we can assume that the total plate exposed to be laminar flow. This is very important. How? See. So first step is that to check whether the flow is laminar or turbulent boundary layer. This we take. Laminar or turbulent boundary layer. So for that we have to calculate the critical Reynolds number. What do we calculate? RECR we have. For the plate, what if we have? Velocity U XCR divided by nu of air. Yes or not? Now, and what is this critical Reynolds number? 5 cross 10 to the power 5. Now, if we calculate this XCR, critical length, this is called XCR, and this length XCR, if you calculate the velocity, it is U, it is given, right? Kinematic viscosity, it is given or not? Yes, kinematic viscosity of the air, it is given, right? Nu, it is given. Nu of air, it is given, beta, how much? 1.5 cross 10 to the power 5. It is given. So from here, if we calculate this value is 7.5 meter. Now, this is your critical Reynolds number. This is your critical length. That means, see, if there is any plate, this is your, let's suppose the plate length is, let's suppose this plate length is, X is, let's suppose 6 meter. Now, if this is a 6 meter, now your critical length is 7.5 meter. That means this length is less than XCR. So what are your assumptions? The assumption is that over the plate, the fluid is laminar. Now, if this X is, if this 6 meter is greater than XCR, that means at the 6, that means greater than 6CR, that means at the XCR there is a laminar, after that there is a turbulent. That means it is the laminar and turbulent both. At critical length, what is the critical length? This critical length, that means up to this length the flow is laminar. Up to this length the flow is laminar. So if the XCR is less than this dimension, that means at this dimension the flow is laminar, but after that the flow is turbulent. Now, if there is a 6 meter is less than XCR, so we can say that the whole plate over the plate is the flow is laminar. So this is XCR. Now, what is the total length of the plate? First we calculate it. What is X? First we will calculate the X length. So how to calculate X length? See, X is equal to, this is Y, let's suppose this is Y, and this X is what? See beta, we take an element. Why? Because flows flow in this direction. So this is our element, very important, right? This is length is dy. Okay, this length is dy. This length is dy at y. Okay, and at y, this is dy. Okay, and this is you take this is your x distance. What is the distance? X distance. So x length of the which take a element of the length x and width dy and width dy. So what is the x, beta? What is the x? See, what is the L? This is your L. Let's suppose this is your L. So if you take this, so this is L by 2. This is, if you take x is equal to, that means if you take tan theta, so this tan theta is equal to what? This is tan theta. This is also 30 degree. So x is equal to y, this y length, this y minus L by 2 divided by minus tan theta. This is yes or not? This is yours or not? That x tan theta, this is your tan theta, na? Theta, na? If you take theta is, if you take, this is our theta, so this is L by 2, this length is L by 2, right? This is L by 2, okay? This is y, okay? This triangle y, so L by 2 minus y, yeah, L by 2 minus y divided by tan theta. So what is the tan theta is here? That means what is the x here? If you write in positive, L by 2 minus y, that means L by 2 minus y divided by tan theta. Tan theta. That means x tan theta, if you write tan theta here, tan theta is equal to what, beta? This tan theta, if you write, this is theta, okay, x. So tan theta is equal to L by 2 minus y, this if you theta, L by 2 minus y divided by x. So this is tan theta. So this is your x. Now put all this value. Theta it is given 30 degree. Okay. Y it is given or not? This is y. Okay. So you can find here x value. Y, put y is equal to 0. See, we have to find this length, na? This is the length, na? You have find this length, na? This total length of the plate. So this total length of the plate, if you find, at which y equal to 0, here y equal to 0, this point is y equal to 0. So put y equal to 0 here, y equal to 0 here, L by 2 you have. So this x is equal to c. If we put y is equal to 0, see the beauty, if you put y is equal to 0, automatically x converted into x max. Why? Because this is negative y. So if we put y equal to 0, this will convert into x max. X max. And what is the x max? Is the maximum length is equal to what, beta? L by 2 you have, yani this means 1 divided by 10 30 degree. 1 divided by 10 30 degree is how much? 1.73 meters. See the beauty. That means x critical is a much higher than, that means beta, x critical is a much higher than the length of the plate. Length of plate. That means the flow is fully laminar. That means the fluid which is flowing over the plate is laminar. The fluid which is flowing over the plate is laminar. This is very important calculus, I am telling you. So we have to say that, ki sir, x CR is very, very greater than X max, that means we can say that, sir, that means laminar at the entire triangular plate. Yes or not? That means X is the laminar at the entire plate. Now, what is the drag force? How to calculate? So, what is the drag? If you calculate this one, drag force, if you calculate this one, drag force, so this is your dF, that means this F is how? Calculate FD integration. So this is your FD. So FD is what, beta? FD, dF is equal to this CD into half rho u square. Yes or not? Yes or not? Drag force. Oh, there is a little bit mistake here. See, this is a pressure unit, na? So pressure of force upon area. Pressure barabar force upon area. So if you write area, so multiply here area also, beta. Multiply here area. So if you calculate the drag force, CD into half rho u square into area which is selected. What is the area selected? Dx into 1. Dx into 1. Why? Because this is force. Okay, and this is stress. So this is also Newton per meter square. This is also Newton per meter square. But this is Newton. And this is Newton per meter square. So Newton per meter square into meter square. Cancel it. So it is Newton. Non-dimensional number. It is right. Okay. Now, so if you calculate dF, d drag force, integration CD half rho u square into area. What is the area? This plate area. What is the area of this plate? What is the area of this place? dy into x. Yes or not? dy into x. This is the area of the plate. X into dy. This is your x into dy. This is the drag force. Now, the drag force CD. So this is on integration. This is your dF. Now we can integrate. So this CD is what, beta? This CD you have 1.328 divided by REL, right? Entire plate. So this is your 1.328 divided by RE power 1 by 2, right? Okay, no problem at all. So what is the value? 1.328, and what is the RE? RE is what? Square root. So this is your U by nu ka whole 1 by 2. Yes or not? Into this is, if this is your at any x, this is your x, na, so put x here. So and x is this is your x, and x power 1 by 2. Okay. Now into this one, half rho u square into this one, x into dy. This is the calculation. Okay. Put this one. Now you arrange. If you arrange this thing, this thing will come. This thing. If you arrange this thing, this will come out to be 0.664 square root of nu rho u in u pe power 3 by 2 x pe power 1 by 2 dx. This is very important. Now you have to integrate. Now the total drag drag FD is equal to integration of dFD. Now both the plates, so multiply 2, right? So first phase, second phase, so multiply the 2, back, the back 2, front 2, yes or not? This is 2 na, see, back and front, okay. So this is 2 into integration 0 to, see, we have to take origin here, or we take origin here. So 1 and 1/2, 1 face bottom and top, one face is back side and front side, so there is 2, other is back side and front side, so there is 2. So if you take it from here now, we integrate from 0 to, here is a 0, 0 to L by 2, 0 to L by 2 integration, but how we will multiply? There are 4 faces, 1, 2, back side, 3, back side, front. 1 is front, this 1, other is back for this top portion, 2, 1 is front of this lower portion, 3, other is the back portion of this lower portion is 4. So there is a total 4. Why? Because origin is taking this side. So this is very careful. 2 into, now integration of this one. So integrate 0 to L by 2 into this D, FD. Okay. So put this value. So total drag FD is equal to 4, 0 to L by 2, 0.664 square root of nu rho u per power 3 by 2 x per power 1 by 2 dy. Okay. And what is x? These are two independent. How to integrate? So we know that x is equal to what? X is equal to L by 2 minus y divided by tan theta. Put this value. So this is your FD, 0.664 outside, 0.664. Put all the things, multiply with the 4, integrate it. So it is like that, 0.626 rho within bracket, okay, UL per power 3 by 2 square root of nu by tan theta. Okay. Now density, this is air. So density of air, we know that 1.23 kg per meter cube. Put all this value, density, U, L, mu, tan theta, and it is come out to be 1.1 cos 10 to the power minus. This is your drag force, FD. This is your drag force. This is the drag force. Okay. So I hope this is a very good question. All the concepts, all the formulas here. So what is the skin friction? Skin friction, a drag, right, over the plate. What is the drag? Okay. So this is your drag. This is your drag. Okay. This is not this one. Okay. So you have to find it, this value. From this value, you have to find all the things. Okay. This is okay, no problem. So this is the nature. First, you have to decide whether the flow is fully laminar or turbulent, so that you can apply it. Okay. So this is your for laminar. Okay. We assume that the plate, over the plate there is a flow is laminar, so that we can use it. Okay. The flow is laminar. So these all are CFX and CFL. This formula CFX 0.646 cross divided by REX by power 2. This is for laminar. 1.328 divided by REL by power 1 by 2. This is also for laminar. So we have to check it. Hello, Nikhil. So we have to check it whether the flow is laminar or not. For that, we if we check the flow is laminar or not, for that we have to calculate the critical Reynolds number. That means critical length at which below this length the flow is supposed to be laminar, above this length flow supposed to be turbulent. So we just compare it. The length maximum is 1.3, that means this plate maximum length is 1.3, but the critical value is 7.5. So obviously this critical length is much higher than the length of the plate. That means the up to this critical length the flow is laminar. But if this is our plate, right, if this is our plate, this is our plate, and over that plate the flow is laminar. The flow is laminar, but our length is this much. Our length is the length which is the flow up to this. That means over the plate, above the plate, leading edge, above the leading edge, yeah, outside from the leading edge, the flow is also laminar. If we extend the plate up to 7.5 meter, the flow is supposed to be laminar. The flow is supposed to be laminar. Okay, the flow is supposed to be laminar. So that we can assume this. This is the concept of critical distance. Along that we have to calculate it. Okay, beta? Okay. Now I give you another things. What is that? This is very important. What is that? So this is something we have to suppose to 100% there is a chance of the question which to be asked in the examination. Okay. Now we have to find this equation. What is that? This is a very important equation. We have to find. I'm not solving about that. I'm not solving any. I'm not deriving anything. I'm not supposed to be discussed here in the. You have to study. No, I have to give the one crisp and subtle concept so that you can boost in your examination. Okay. So what is that next one, Rita? See, if you take a fluid element, okay, if you take a fluid element, that means this is our fluid element. This is very important, I'm telling you. This is our fluid element, okay. Let's suppose this is our fluid element. If you take this is our fluid element, okay, and it is element, this is a fluid element, that means this is a fluid element. Fluid element at time t. Okay, beta, this is the fluid element at time t. Now, at time t plus delta t, this element will deform, obviously. That means, let's suppose after the t plus delta t, this element will deform like that. This fluid element will deform like that. Okay. So this is a deformation. This deformation, that means element t plus dt. Okay, t plus dt. This is the element at t plus dt. No problem at all. This is called general motion. What is that? General motion. This is called general motion. Okay. Now, how this general motion is supposed to be combined? How we think that this general motion is supposed to be combined all the motions? See, this motion is equal to, there must be a fluid element which may be, this is a fluid element, see the beauty, this is the fluid element, this is the fluid element which will translate. This is your linear translation. This fluid element which may be a linear translation. So this is your translation. Why it is back dotted? Why? Because you supposed to that there is a fluid element and that fluid element is moving linearly. So you don't see that. So this is your dotted line. This is the fluid element, this is the fluid element, and this fluid element is moving. That is called translation motion. Okay. So this motion is translation. Okay. And translation with a velocity v vector. Okay. This is the translation motion. Okay. Now plus there is a linear deformation. That means this is our fluid element. See the beauty. This is our fluid element. This is our fluid element, and that will deform linearly. That means it may be like that. This fluid element will deform like that. So this is linear deformation. Okay. Linear deformation. This is your linear deformation. Okay. This is your linear deformation. Okay, beta. Now plus, see, this is your translation, this is your linear deformation. That means stretching of edges. Okay, this is your linear deformation. Okay, that means this is your body and this will stretched, linearly stretched. See, this is linearly stretched. Now there may be rotation, rigid body like motor. That means this is your body. Let's suppose this is your body. Okay, and this body will rotate. This body will rotate like that. Okay, see the beauty. See the beauty. This body will rigidly rotated at this angle. This will rotate. That means this is a rotation like that. Okay, this is a rotation. So this is a rotation. This is a rotation, rigid body like rotation. Okay, this is a rotation. Okay. Now the other thing is that there may be a angular deformation. There may be a angular deformation. What is that? See, if this is a fluid element, if this is a fluid element, it may be deformed like that, angular deformation. That means this edge will tilted, this edge will tilted. So this may be a angular deformation. This is the angular deformation. Okay, angular deformation. Angular deformation. This is angular deformation. So beta, see, if there is a fluid element which will deform like that after t plus delta t, what is the possibility? There is combined of all these things: translation plus linear deformation plus rotation plus angular deformation. So beta, there are three terms which is very important. That means if you take in the form of coordinate, beta, how will represent? See, very important. See, if this is our y-axis and this is our x-axis. Okay, this is our x-axis, and if this is our fluid element, okay, this is our fluid element, that means this we consider now, this time if we consider a particle, that means this is a particle at time t. Okay, now after some time this particle is look like that. After some time this particle is look like that. Okay, so this is your particle at time t plus dt. No problem at all. No problem at all. Now this is the general, in general motion. Now if we suppose to, this is your x and y axis plus this is your y x axis plus this is your y and x axis plus this is your y and x axis. Okay, there are four combinations there. Okay, so this is your y, this is x, y, x, y, x, y, x. Now if this is our fluid element, if it will translate, very important, so it is like that. After some time the fluid is reaches here, no problem at all. So this is your translation, this point shifted at this point. So this is your translation. So in this case the velocity, it will move in x direction also, it will move in x direction also, and it will move in y direction also. Okay, so in this case the translation, there is a translation. So in this case if you suppose u and v, we can also write ux and uy. Okay, this is your translation. Okay, this is your translation. Okay, now there must be a linear deformation. How it look, how we'll say the linear deformation in the form of particle? This is our particle, this is your particle, and let's suppose it will deform. It will deform, that means stretched. So this will deform, let's suppose there is a deformation, it will stretched, this is deformation. Okay, so those, see the volume is same. In this case volume is not changing, volume is same, volume is not changing, my dear. So what is that? What do we find here? We find the rate of volumetric strain. We find rate of volumetric strain. Rate of volumetric strain. That means how to denote? Del dot v vector. Del dot v vector. And del dot v vector, how we'll write? In x and y direction. That means dou u by dou x plus dou v by, that's it. Okay, rate. So in the case of, this is your linear deformation. Okay, linear deformation. So if the fluid is linear deformation, we check the rate of volumetric strain simply. That means if the volumetric strain is 0, there is no any linear deformation. If the volumetric strain is there, there must be a linear deformation. Okay. Now third is rotation. How to define? See, this is your fluid particle, and this particle will rotate. That means this is same, and just only it is in this shape. There is no any. So this is a rotation. Okay, this will rotate like that. this will rotate. Okay, so this is rotation. This is rigid body rotation. Rigid body rotation. It is rigid body rotation or not, we have to find vorticity. What we find? Vorticity. And what is the vorticity? We have to find omega rotationality half of del dot v vector, right? And what is del cross or? Half del cross v vector. And how to find del cross v vector? That means if you find omega z, why? Because this is x and y. So rotational component is in z direction. So omega z is equal to, just opposite and put negative sign, dou v by dou x minus dou u by dou y. This is very important, I am telling you. One question is must you have to find in this topic tomorrow. So this is your vorticity. So if this is 0, there is no any rotation. If this is non-zero, there must be a rotation. If there is a non-zero, that is called irrotation. If it is 0, this is called rotational flow. That means the flow is rotating or not, it will depends upon the vorticity. It will depend upon the vorticity. So vorticity, from the information of vorticity, we have to define, we have to judge that the body, that means a fluid, a particle will rotate or not like a rigid body. Now, if we think that the fluid element will deform linearly or not, we will check the volumetric strain rate. Okay. Now, if the velocity is given in x direction or y direction, there must be a translation, linear translation. Okay. So now the fourth thing is angular deformation. Okay. So fourth thing is what? Angular deformation. How to find the angular deformation? Very important, I am telling you. Angular deformation. So this is your particle. This is a particle, and angular deformation is what? This is like that. It is like that. This is angular deformation. 1 second. We make like that, no problem. This is angular deformation. So this is your angular deformation. And we have to find angular deformation we have to find, how to find the angular deformation? We have to find the rate of shear strain. How to find rate of shear strain? Rate of shear strain. Rate of shear strain denoted by gamma dot. And this gamma dot is this one but positive sign. That means dou v by dou x plus dou u by dou y. This is very important, I am telling you. So if the particle will general motion, that general motion is the combination of 4 possibilities. One is the translation, one is the linear deformation, third one is the rotation, rigid body, and fourth one is the angular deformation. If you find the linear deformation, just you go through the information of volumetric strain. What is the volumetric strain? Sir, velocity gradient in the velocity gradient in the x direction and velocity gradient in the y direction. Velocity gradient in the x direction means dou u by dou x, velocity gradient in the y direction. Okay, dou v by dou y. This is the y direction, this is your x direction. Now, if the body is rotation, that means a rigid body like rotation, we go to the vorticity. You go through the vorticity. From the vorticity, we have to check del cross v. So, if omega z is equal to 0, what is the omega z? Just reverse and put the negative sign. If omega z is 0, the flow is irrotational, and it is non-zero, the fluid is irrotational. Okay. Now there is a last is angular deformation. In the angular deformation, what we found the shear strain rate. And how to find the shear strain rate? Velocity, change in velocity with respect to x, if velocity in y direction with respect differentiation with the x direction, plus velocity in x direction, differentiation in y direction. Add them, you have to find this one, whether it is 0 or not. So this combination is very important, I am telling you. For that, we have one problem. What is that, beta? See, this is very important. What is the problem is that, see, you know that coat flow, there is a coat flow is there. That means this is your fixed plate, this is your fixed plate, and there is a plate which is moving, okay, which is moving with the velocity u, okay. Now, the gap is h. What is the gap? This two plate, the gap is h. That means fluid flow due to displacement of a boundary. The fluid flow due to displacement of a boundary. We take any coordinate. This is velocity u. Due to no slope condition, the velocity is 0. We draw like that. So this is your velocity profile. What is the profile? What is the profile? U, which is in x direction, variation in y direction, is equal to linear u y by h. U by h. Right? U y by. So this is your situation. Okay. See, the profile is any type, it is given, but we take a simply, that means this is your coat flow. What is that? Coat flow. And what is the characteristic of the coat flow, beta? What is the characteristic of the coat flow? No pressure variation. No pressure variation along. Yeah, pressure is that means dou dp over dou p over dou x is equal to 0. That means no pressure variation in x direction. This is x direction. This is y direction, and this is x direction. Right? Number first. Number second. What is the property of coat flow next? What is the next property? Shear stress is constant. There is a shear stress is constant. Yani tau shear stress is constant. There is no any shear stress variation. That means each and every layer have a fixed shear stress. That means what is the shear stress here? The same stress is here. You have to find it, no problem. How to find? Newton's tau is equal to mu du over dy. Put here mu du y khatam u by h. So this is your constant. This is h is constant, mu constant. So shear stress is constant. So constant shear stress distribution. There is no any shear stress. So these two property is the coat flow, and the fluid flow. Fluid is flowing due to displacement of a boundary. Due to displacement of a boundary. Fluid is flowing due to displacement of a boundary. Now, what is the condition? What question will ask in the, this is in this portion, You must be thinking about that MSQ type question. MSQ. This is your MSQ type question. What is that? Ki sir, first you find this one. That means the fluid is linear deformation or not. Okay, fluid is linear deformation or not. Okay, so we have to find fluid have linear deformation. Okay, now if the fluid have a linear deformation, it is right or wrong, we will check. Okay, so for that we have to find volumetric strain rate. Volumetric strain rate. That means volume change, there is a volume change for the fluid element with respect to time or not. Okay, that means change in volume of fluid element with respect to time. Okay, time or not, we have to check it. We have to check it. So for that, what we find? We find del dot V. So we have to find del dot V vector. Okay, what is del dot V vector? Dou U by dou X, dou V by dou Y plus dou omega by dou Z. See, this is one dimensional flow. This is one dimensional flow. Okay, this is one dimensional flow. So this value is 0 and this value is also 0. Why? Because U is the function of Y only. So there is no any V 1D flow. Okay, and U is the function of Y, so it is also 0. So del dot V is equal to 0. Del dot V is equal to 0. That means fluid have a linear deformation. That means that see, if this is 0, that means it is how, why it is this is, that means there is no any change in volume. Yes, no, not deformation. That means change in volume of the fluid element with respect to time or not, we'll check. This is 0, that means change in volume with respect to time is not true. That means it is non-deforming fluid. That means the volume of fluid element is not changing, with respect to time. That means non-deformation, non-deforming fluid, right? And this is true for also incompressible fluid. So what is the property? The property is that court flow, the third property of the court flow is that the fluid is non-deforming. The fluid is non-deforming, right? Okay. Now, second, what is that? we'll check second, we'll check, that means cot flow, this is 0, that means there is no any volume change. Now we'll check the fluid element is rotating or not, that means it is rigid body rotation or not. So we'll check omega z. So what is that? Okay, option, so it is, yes, it is deformation. Option B, no deformation. Yes, option B, angular motion. That means we have to find the fluid is rotating or not. Very important. If the fluid is rotating, that means this is a rotational flow. Rotational flow. If the fluid is not rotating, it is called irrotational. Right. If the flow is rotation, that means omega z is not equal to 0. If the fluid is rotation, that means omega z is not equal to 0. If the fluid is irrotation, that means omega z is equal to 0. If the fluid is rotation, that means the fluid irrotation, that means the fluid is not rotating, right? The fluid is not rotating. If the fluid is not rotating, the component of z direction velocity is 0. Why? Because fluid is fixed. If the fluid is moving like a rigid body, see this is a fluid, see beta, if right, this is a fluid, right, a fluid element, and it will move like a rigid body. It will move like a rigid body, so there is no any, so that means it is a rotational flow. If it is not moving, that means this is a irrotational flow. We'll check for the cot flow. So we have to check omega z. We have to check omega z. What is the omega z? Half into vorticity v vector. This is your vorticity, okay, and this is your half. How to calculate? I j k u v omega dou by dou x. No, not like that. This is your dou by dou x, dou by dou y, dou by dou z, u v omega. Put all this value. So half I j k dou by dou x, dou by dou y, dou by dou z, what is the value of u? Capital U by h 0 0. If you calculate, this is equal to minus u by 2h k vector. Okay, that means omega z is equal to, if you write omega z direction, that means u by 2h anti-clockwise, counter-clockwise. That means it will move like that, okay, anti-clockwise. That means it is clockwise, sorry, it is clockwise. That means into the board, omega z is into the board. Out to the board is it anti-clockwise. This is clockwise, that means in this direction. It will move in this direction. Why? Because omega z is negative. That means it is rotational flow. What is that? Rotational flow. Rotational flow. It is what? Rotational flow. That means if you displace the boundary, that, see, yes, it is obvious. If this is your plate and this is your fluid, this is your fluid, and if you put the plate over, drag the plate, there may be a chance. See, this is your fluid element, this is your fluid element which is stick, this is a fluid element, this is a fluid element. So lower is the fluid element, it is also fluid element, fluid element, fluid element. It is look like that. Okay. Now if you drag, so we develop the tangential motion. That means this fluid element have a tangential motion. Okay. U. So it may be rotate. This fluid element have a tangential motion. U. So U. So it may be rotate. So it is a rotational flow. Okay. And this is in this direction. So rotational omega z component is into the board. What is the direction? Into the board. Thank you, Bhavya. Okay. So it is your into the board. Okay. So this is your omega z. That means a flow, rotational flow. Now, so we have to check the chord flow. This is your chord flow. This is your chord flow. So the chord flow is, it is your non-deforming fluid. It is not deformation. Ram Krishna. Hello, Ram Krishna. What is that, sir? Is heavy fluid mechanics engineer? I cannot understand. Ram, I cannot. Sir, is heavy? Okay. You just what you asking? Just clear that. Okay. So this is your non-deforming element, but it is rotating. It is rotating, and a u velocity it is given. No, it is little bit tough, beta. Babya, it is little bit tough. It is not like that a previous 2022. Previously 2022, why the question is level is low? Why? Because there is a COVID. Due to COVID, the question is not up to that level. But in this time, the question is very high level. So prepare for that. Each and every point you just think. In this season, tomorrow there is a GATE question in the GATE paper second half. So be prepared for. I am not more demotivated. Your preparation is very good, Bhavya. Your preparation is very good. You don't think that, yes, sir, I'm not preparing like that. No, your preparation is very good. Go through that. No problem. Don't study. Just go to the very good slope. No, don't bother about that. But you just think that you have very performance, the very intelligent performance in your GATE. When you are writing the GATE paper, very intelligent. Why? Because very conceptual question I am expecting. Okay. So be prepared for that. Okay. So for that, sir, 2022 60 marks. No problem. 60 mark is tensed, but in this time, see, I'm not personally talking with Bhavya. I'm talking with the, what is the approach in this 2023 as compared to 2022. See, beta, 2023 examination, you have to should be very intelligent performance during 3 hours. Because such type of question that you have to see that it is very easy, but while solving, there is a lots of confusion is there. Okay. So very intelligent question is expected to coming there. So such that we are revise like that. So you don't confuse for that what is the question is asking. Okay. So the question level, it is not very tough question, but the way of the asking the question is also the very confusing in this upcoming examination. Okay. So be prepared for that. Now, now the third is, so what is the chord flow? Chord flow, the pressure gradient is 0, shear stress is constant, and fluid is flowing due to displacement of a boundary, and there is an incompressible fluid, and there is a non-deforming fluid. Okay, these are the property. and this is a rotating fluid, very important, and this is a rotational flow. Now, that means during the quad flow, the fluid rotate like a rigid body. Fluid rotate like a rigid body. Now, we should have to, okay. Now, we have to take that it is angular deformation or not. That means this is B, option number C. We have to check. We have to check C, angular deformation or not. Angular deformation or not. We have to check angular deformation or not. How to check the fluid is angular deforming or not? So we have to check shear strain rate. Shear strain rate. We have to check shear strain rate. What is the shear strain rate? Gamma. What is that? Dou V by dou X plus dou U by dou Y. So dou V by dou X, this is 0. Dou V by dou Y, U by H. So this is your U by H. So beta, there must be a shear strain rate. That means this is an angular deformation. That means this is not 0. That means it is U by H. That means there must be an angular deformation. Okay. Angular deformation. Okay. There must be angular deformation. There must be the please let's teach. Don't ask much. Okay, okay. Yes, yes. Okay. Yes, 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 yes. Babya, very careful. Don't ask anything. Just learn. Okay. What is your preparation? It is your good. Okay. So this is your angular deformation. Now, sometime in the D, you may ask that what is the vorticity? Vorticity. So vorticity denoted by ipsila, and this ipsila it is your 2 into omega. What is the omega we have? What is the omega angular velocity we have? What is the angular velocity? U by 2h. So multiply with that 2. So 2 cancel. So U by h is the vorticity. Okay. So U by h is the vorticity. That means minus U by h in k direction is the vorticity. Okay. So what is the question is asking is that, sir beta, so what is the summary? If you have any profile is given, now what is the summary beta? Very important. If there is any, so what is the given condition? You have to a velocity profile is given, right? Velocity profile. In general, linear or parabolic. Linear or parabolic it is given. Now, and in this question, there are 4 possibilities to ask that. What is that? Is the fluid is what is that question? Is the fluid is volumetric, volume will change or not? Volume will change or not with respect to time. Mind it, with respect to time. That means rate of volumetric strain. Number second, you have to find fluid is rotating or not. Rotating or not. And that rotating or not, it is a rigid body like rotation. Okay. Now, third thing you have that the fluid is angular deformation or not. Angular deforming or not. Okay. Fourth thing is that asking vorticity. So please keep in mind how to calculate these things. So volumetric volume will change with respect to time, volumetric strain. Rotation, you have to find omega. That means in this case, you have to find volumetric strain. Volumetric strain rate, right? Rotating or not, you have to find omega z, omega x. What is that? Angular deformation or not? Angular deformation or not? You have to find shear strain rate gamma dot. Vorticity, you have to find epsilon is equal to 2 into omega z. This is very important. So in this portion, must be one question will ask in the tomorrow. It is not, I'm not like that I'm setting the question, but it is in this portion must be one question you see in the examination, okay? Either in the mechanical or civil or both. Okay, so tomorrow is the mechanical session, so must be watch this concept. Okay, and previously there must be a drag, and what is the drag, and what is the friction drag, what is the pressure drag, and what is the drag coefficient, how the friction coefficient is calculated, and there must be some question also. Okay, so this is our next thing. Now there must be one thing, Vita, I will wish you. Now, there must be one question will ask during the flow through pipe. During the flow through pipe. What is that, Vita? See, what is you have to remember during the flow through pipe must be. What is that? See, this is very important. What is that? See, if Reynolds number, we know that internal flow, if Reynolds number is less than 23 or 2000, we may be right. There is a 2000, there must be a laminar, no problem. There must be a laminar, no problem. Now, we know that when this is your pipe, beta, if this is your pipe, okay, and the fluid is flowing, during this flow, the pressure must be decreasing. That means in this direction, the fluid is possible when the pressure is higher pressure. That means in this direction, this pressure is high pressure, and this is your low pressure, so that the fluid is flowing. So, due to loss in pressure, why the pressure will lose? Due to why the pressure, that means the energy, pressure energy at this point is higher, and while the flowing, the pressure energy is lower. Why? Why? Because the fluid have a viscosity. Why? Because fluid have a viscosity. That means pressure must be decreased. Pressure must be decreases. Pressure must be decreases in the flow direction. In the flow direction. Okay. In the flow direction. Okay, beta. In the flow direction, because of viscous effect. Because of viscous effect. It is very clear. It is very clear. Why? Because the pressure will decrease in the flow direction. Why? Because there is a viscous flow in pressure. That means we have to look at such type of the phenomena in which the flow through pipe a viscous fluid. Okay. So there must be a pressure drop delta P. This is called pressure drop. pressure drop. This is length L. Let's suppose there is L length of the pipe. There must be a pressure drop. How to calculate the pressure drop? This is the genuine formula, 32 mu V average L by capital D square. This is the diameter of the pipe, capital D. Okay. This formula, this pressure drop is 32 mu V average by L. Mu V average L into D square. This is very important. This is only used for laminar flow. Laminar flow only. This is very important. But it is not like that. Always the flow is laminar. It may be greater than 2000. So first we think that the flow is laminar. That means it is less than 2000. Let's suppose. So this is okay. Now this pressure drop is due to, why the pressure drop is there? Due to, why this pressure drop is there? Due to viscous effect. Why it is there? Due to viscous effect. Okay. Due to viscous effect. This drop in pressure is written as a, due to friction, that means pressure loss. Due to viscous effect, this drop in pressure is loss. It is permanently lost. So this viscous effect, there must be a loss in pressure. And how to calculate? Delta P loss is equal to the friction factor F L by D into rho V average square divided by 2. So this is another kind. And this equation, due to viscous effect, loss in pressure, delta P, see this is also pressure loss, but due to only laminar. This is also pressure loss. This is the pressure loss, is also the pressure loss, and this is applicable for both laminar or turbulent. For both laminar or turbulent. This is for both laminar or turbulent. Now beta, how to calculate F? How to calculate F? This is a friction factor. How to calculate F? This F is equal to 64 by RE. Very important. Mind it. And what is the condition for this one? Circular pipe, not rectangular or other than circular pipe. That means this is for circular pipe with laminar flow. Other, if there is a circular pipe but the flow is turbulent, this friction factor is given, no problem. Don't worry about that. Okay. So from that one we have to calculate the pressure drop. Okay. So my dear, if you ask me, sir, which we will use for the more accurate result, we always prefer for that. Why? Because in that there is a friction factor is calculated, consider. Okay. So this is your pressure loss. This is also pressure loss, but this is the flow is only laminar. But if you apply this is very accurate relation. Okay. So always go through this F L by D rho V square upon 2Z. Okay. So go through this formula and mind it, you check that the pipe is circular or not. If the pipe is circular, then flow is laminar. Okay. This is the pressure loss. Now once you find the pressure loss, you have to find the head loss. So once you find the pressure loss, this pressure loss PL divided by rho by G, this is your HL, and this HL is called head loss. What is called? Head loss. Head loss. What is called? Head loss. What is called? Head loss. So flow through pipe, if the Reynolds number is less than 2000, flow is laminar, so pressure must be decreased, but the pressure must be decreased during the flow direction because of viscous effect. So what is the pressure drop? The pressure drop is 32 mu V average L by D square. This is only for laminar, but if the flow is turbulent or another that turbulent, so due to the viscous effect there is a pressure loss. That means there must be a pressure loss, there must be a pressure loss, but this pressure loss is due to, this pressure loss is for laminar and turbulent. What is the, these are the both are the same formula. These both formulas are due to the pressure loss. Pressure drop या pressure loss. Pressure drop या pressure loss are the same thing. Why? Because the viscous effect. But this pressure loss formula is only for laminar, and this pressure loss is formula for laminar and turbulent. So go through this formula only. Okay. Now here from the friction factor F 64 by RE, 64 by RE. Why? When we apply the 64 by RE, the pipe is circular and the flow is laminar. Now this delta P by L, if you divide it by rho G, this is called head loss. So successfully you have to find the head loss. Now once you have find head loss, very important. Now head loss you have to, okay, HL, now you have to find it, no problem. Head loss you have, this is your head loss. Head loss, that means head loss you have. Now from the, see, if you have the head loss, so what the question is asking, what is the required power, pumping power? That means to compensate this loss. What the extra power will required? Why? Because when the fluid is flowing, there must be a losses. So that losses, equivalent to that loss, what extra power will required? That is called pumping power. So required pumping power, required pumping power you have to find it. Okay, required pumping power. And why we required to pumping power? To overcome the pressure loss. To overcome the pressure loss. This pressure loss to overcome, to require the pumping power. How to what? See, very important. This is the power. So energy per unit, joule per unit second. So this is W dot pump. And this pumping power is required due to loss. Due to loss. What is that? Volume flow rate into delta P L, pressure loss. Right? This is the volume flow rate you have discharge. What is the delta P? Rho G into HL. You have HL. Now, right, beta? See, what is this V? What is this V? V is volume flow rate, meter per second. Okay. Into, what is this? Force per unit area. That means Newton per meter square. Okay. That means what is this? Newton meter per second. Okay. And Newton meter is what? Energy. Newton meter is what? Newton meter. This Newton meter is what? Energy. That means energy per unit second. This energy per unit second is what? Power. is what? Power. This energy per unit per second is what? Power. So pumping power, you have to multiply discharge volume flow rate into pressure loss. Okay, right. And very important thing is there, this how to find, this is your mass flow rate. If the mass flow rate is given, mass flow rate G into H into L, these are the same. These are this mass flow rate. This is your mass flow rate. Okay, this is your mass flow rate. If it is given, mass flow rate, that means it is volume flow rate is not given, mass flow rate is given. So just mgh. This is very important. I'm telling you. If there is no any volume flow rate, it is given. So just go mgh, potential. It is like a potential. From this, you have to calculate the pumping power. Why have you calculate pumping power? To overcome the pressure loss. Why the pressure loss is happening? Due to the viscosity, viscous effect. Okay. Now, so this is all about the pumping power. Now the second thing is, we have to discuss about that. B. See, what is the delta P for the laminar? 32 mu V average L by D square. Okay, beta. Now what is the V average here? We have to find V average here for the laminar. If the flow is laminar, so how to find the V average? Delta P D square divided by 32 mu into L. Okay. Now how to find the volume flow rate now? How to find the volume flow rate now? Volume flow rate, this is a volume flow rate, is equal to, we know that discharge is equal to area into velocity. That means average velocity into cross section area. This is volume flow rate. What is the average velocity you have? Delta P D square by 32 mu L into, you have cross section area, pi by 4 D square. You multiply it. So volume flow rate, it is your delta P pi D pe power 4 divided by 128 mu into L. Why this known as? This is called Poiseuille's law. This is known as Poiseuille's law. Why this formula is important now? See, why this formula is important? This is very important information. Sridhar, good evening, beta. Why this formula is important? Anyone? Why this volume flow rate is very important? Why? Because see, sometime there are pipe. This pipe is given, and this pipe, let's suppose this pipe have a diameter 2 meter, and discharge is 3 meter cube per second. Now, if we change the diameter of the pipe up to 4 meter, what is the diameter will change? What is the discharge will change? How the discharge will change? Yes, it is not hard and tough. It is a matter of you are prepared of this level or not. This is not a matter to hard and tough, beta. In a life, you always remember Salend. It is not a matter of hard or easy. If you think about in the life, there something is hard and something is easy, you have never achieved. It is a matter of your performance. Yes. No, it is not. It is yes, but variation is, it is hard or low. It's up to you. Okay, it is up to you. It is yes, but it is variation is hard or low, it is up to you. Why? Because if there is a gate, some student will score good marks and some student would score very poor marks. 85 marks, it is good. 85 marks, that means you have to select it in PSUs. 85 marks, it is selected in PSUs. No problem. It is not a question to asking. It is self-justified. Okay. So this is possible. So if there is a 4-meter pipe, there is a 2-meter pipe, there is a velocity 3-meter cube, and there is a velocity, how to find the volume flow rate? Just you go through the, that means during the pipe flow, you always remember the discharge is directly proportional to d ke power 4. This is very important. Discharge is directly proportional to diameter per power 4. And discharge is inversely proportional to length of the pipe. This is also, these two relation always remember, beta. These two relation is always remember. IIT Patna, it is not, Sridhar, it is not a matter to 85, in 85 marks, you need not to go to IIT's Patna, better than IIT's Patna's. Even you call, maybe enter into IISc Bangalore, no problem. IIT Patna demands a very low marks. If you just qualify, if you change your field, if you know any existence, yes, if you change the field, there is no any existence. Okay, be focused. Okay, tomorrow is exam. Talend, you have examination tomorrow or not? First, give me a result, reply. You are a mechanical student or civil student? So this two formulas is very important. Okay, Q is inversely proportional to length and Q is directly proportional to the diameter. So you have to always mechanical. So tomorrow is your exam. Okay, tomorrow your exam. So be focused. Don't think like that. Okay, just ask in that this concept. This is a very important concept. I'm telling you. Always you find pipe flow. There is a summary of the pipe flow. Nothing to extra for this one. There is a very toughest portion, pumping power. So how to find the pumping power? This is the major equation. Okay. No. Tension thoda hai. If the tension is little and tension is more, equivalent like that. Tension is tension. Don't feel. Don't feel. जो बीत गई सो बीत गई, तकदीर का सिकवा कौन करे, और जब तीर कमान से निकल गई तो उसका पीछा कौन करे. जो बीत गई सो बीत गई. You don't think, just silent and be prepared and be confident with yourself what you study. Okay, so don't think. Okay, so बीत गई सो बीत गई, तकदीर का सिकवा कौन करे, जब तीर कमान से निकल गई उसका पीछा कौन करे. ओके ओके, हाँ, यस राम, हाँ, बस लिटिल बिट इट इज हिंदी, नो नीड फॉर, इट इज नॉट फॉर टेक्निकल. ओके, आई एम टेलिंग दैट whose things is gone, it is gone. Don't think that it will never come again. What you have, that is better to extend it, to explain it, to modify it and to understand very clearly. Okay, so this is your pumping power required. Okay, now there is one thing is that, beta, when you are, see, now the next question, the next thing is very important is that sometime you have very confusing that, ki sir, how to find, see, how to find the pressure gradient when the fluid is flowing. There is a pressure gradient when the fluid is flowing. There is a pressure gradient. How to find Eulerian equation? Eulerian equation, you have to very careful about the Eulerian equation. There are two equations. One is the Eulerian equation. Yes. See, if there is an equilibrium equation, okay, see beta, in the fluid mechanics, there are three equilibrium. There are three conservation. One is the conservation of mass, other is the conservation of momentum, and third is conservation of energy. So conservation of mass gives the continuity equation, conservation of momentum gives the Euler's equation and Navier-Stokes equation, and conservation of energy gives the Bernoulli equation. So what is the, this equation is very important, conservation of momentum, okay. Conservation of momentum. This is very important. Conservation of momentum. One question is there in the GATE examination. So conservation of momentum, that means this is a force equation. Force equation. And this force equation comes with Newton's second law. Second law of motion. Law of motion. Second law of motion. Okay. Now, this force equation in the fluid mechanics have a two type. That means fluid is, one is inviscid flow, inviscid flow, and second is viscous flow. So the flow is viscous. Yes. I'm not well to clear. If you want to PSUs na beta, you have to score very high. It is not like that you just qualifying and below 50 marks. It is not, never expected to call any PSUs. It is very important, very difficult, okay. It is very difficult, okay. So viscous flow and inviscid. Viscous flow, the conservation of momentum is called Eulerian equation. Euler's equation. Euler's momentum equation. Euler's momentum equation. And viscous flow for Navier-Stokes equation. In the GATE, this is very important. This is very important. In the GATE, this is very important. Okay, Euler's equation, Euler's momentum equation. So how we use the Euler's momentum equation? We just see that. Okay, we just see that. No problem. How we use the Euler's momentum equation? How we use the Euler's momentum equation? See, what is the Euler's momentum equation? See, what is the Euler's momentum equation? See, the motion is in three direction: x direction, y direction, z direction. This is your x, this is your x, this is your y, and this is z. So in x direction the velocity is u, y direction the velocity is v, z direction is velocity is omega. Right? So how to write the सोनू सिंह, गुड इवनिंग सोनू सर, लाइफ में बहुत टेंशन हो रहा है. हाय सोनू, टेंशन तो मुझे भी है. आई हैव ऑल्सो टेंशन. टेंशन, it is not a question, it is not a matter to discussion. Tension, if you have a tension or no tension, it's depend upon you. It is not a matter like that, sir, I have a tension. Everyone in tension. Without tension, the life is not going. If there is engine and the engine is very hot, that the pickup is very high. If the engine is very hot, then the pickup is very high. So if there is a tension, you have to accelerate yourself, okay, so that you are comfortable. Okay, you don't think and always think, so the tension is multiply. Okay, yes. Euler's equation. So what is the Euler's equation? See, Euler's equation. So this is your momentum equation for incompressible inviscid flow, inviscid non-viscous flow, non-viscous flow. That is Euler's equation. That is Euler's equation. Euler's equation. And what is the Euler's equation? And what is the Euler's equation? This is your Euler's equation. Density, velocity with respect to time in x direction, we have talking about dt plus u dou u by dou x plus u dou u by dou v by dou y plus u dou omega by dou z. This is nothing, this is the acceleration, okay, is equal to minus dou p by dou x, x direction, plus rho into acceleration in x direction. This is a Euler equation, simple. That means this is a force, net force into acceleration, mass into acceleration, okay. So this is, okay. Yes, I give you very inside things. What you expend here in a time, that will come into examination. So, Ram, it is very important. What you expend, this is very important for the fluid mechanics, particular. So, if you have a difficulty in the fluid mechanics, just go through that. Otherwise, you are switch off your channel. Okay, no problem. You switch on the YouTube and prepare yourself. Yeah, don't prepare. Just say listen. Don't bother about that. Okay. So this is a viscous equation. Now, beta, what is this? So how to write? I give you one example for that. Okay, I give you one example for that. One second, beta. I have one question. 1 second, I am coming. Hello, my dear. This is the question asked by the student. What is that? See, there is a discharge. There is a pipe, have a uniform cross section, but the discharge is increasing. See, this is the very important, and the question which I am discussing, it is also very important question. Either I don't know it is already asked or not. This is important question. One question asked by the student, so I just explain you. This is very important. Today I just see, and this is very important question to the Navier-Stokes equation. Okay, what is that? So, the question is that there is a pipe of uniform diameter. Diameter is given, and the discharge will changes with respect to time. That means in the pipe the discharge is something at the time t1, and after the time t2 the discharge will change. Increase or decrease, I don't know, just I am giving you. So what is the change in pressure? What is the change in pressure if discharge will change with respect to time? So it is asking that, given, what is the given? Given is very important. Given is discharge, change in discharge with respect to time. Change in discharge discharge with respect to time, it is given. So question is asking that what is the change in pressure? What is the change in pressure? So beta, see, discharge is given and we have to find the change in pressure. We just go through the Navier-Stokes equation. So what is the Navier-Stokes equation? Rho du by, we take x direction, that means pipe, and pipe is horizontal and uniform cross section. This is pipe, and this pipe is horizontal and uniform cross section. Okay, so what is the Navier-Stokes? The fluid is inviscid, and the fluid is inviscid. So it is your apply for Navier-Stokes. So dou u by dou t plus dou u by dou x plus u dou v by dou y plus u dou omega by dou x minus is equal to minus dou p by dou x plus rho into gx, x direction. You always remember this equation. This according to this equation, one question you have to always find in the GATE examination. Okay. Now the flow is one direction, yes or not? That means the flow is in only x direction. This is x direction. Okay. The flow is only x direction. So this is 0. This is 0. This is 0. Why? Because flow is one dimension. Why? Because 1D flow. Yes or not? Why? Because 1D flow. Okay, no problem at all. Now, there is a horizontal. Fluid flow is horizontal. So there is no any gravity. So this is fluid. That means horizontal pipe. Horizontal pipe. So what is your modified equation? The modified equation is dou u by dou t plus dou u by dou x is equal to minus minus 1 by rho dou p by dou x. This is your now modified Euler's equation along the question. So please mind it, write complete Euler's equation and go through the questions, go to the question and think that what is the assumption we have to assume, and accordingly we neglect the sum term and write the fresh equation of the Euler's equation. Now from here, what is your see, now again there is a velocity. So see, this is uniform cross section, yes or not? This is uniform cross section. So what is the value of this cross section? The same velocity at this cross section, the same velocity at this cross section. So velocity is not also changing with respect to x. Why? Because the constant pipe. So this is also 0. Very important. This is not changing. This is 0. Why? Because this is 0. Why? Because pipe is uniform cross section and the velocity remains constant along the flow direction. That means pipe is uniform cross section pipe. So this is also 0. So what is your modified equation again now? Dou u by dou t is equal to 1 by rho dou p by dou x. This is your Bernoulli Euler equation. Okay. Now the second we have asking the what is the change in pressure. So we have to find this. What is the change in pressure? Dou p by dou x. Density, the fluid is given 10 to the power 3 water. So we have to find dou u by dou t. It is very easy to find dou u by dou t. That means velocity per unit time. And how to find the velocity? We know that the discharge is equal to velocity into area. So what is the velocity? Discharge by area. Discharge is given. Area it is given. So velocity. So first, so our task is to find dou v by dou t. Yes, no problem. So dou u by dou t. So dou u by dou t. So velocity, see, velocity is not dependent on the space. See, velocity field u is the function of x, y, z and t. Yes or not? I will write here, no problem. see, u is the function of x, y, z and t. Yes, but this is 0. This direction it is 0. Why? Because one dimensional. Okay, and this is also 0. Why? Because uniform cross section. Uniform cross section. This is 0. So u is the function of time only. Yes, u is the function of time only. So the partial derivative will convert it into absolute derivative, du by dt. So you have to find dou u by dt. Okay, time it is given how much? 3 seconds. After 3 seconds, the discharge will increase. Discharge will increase after 3 seconds. Okay. So okay, no problem. First find du. Du is what? u2 minus u1. So what is u? Discharge q2 by minus q1 by area. Area is same. So what is q2? Discharge it is given. Discharge q2 it is given 100 liter and q1 it is given 25 liter. That means initial discharge is 25 liter. After some time, that means after 3 minutes, after 3 seconds. After 3 seconds, the discharge will increase and it is 100 liter. So q2 you know 100 minus 25 into 10 to the power 3 meter cube, okay, divided by area. Area you have pi by 4 into d. Diameter it is given. Diameter it is given 0.2 meter. That means 20 centimeter. It is given. So from here you can find easily du. You can find easily du divided by time. Time is 3 seconds. So if you find this du, this is your 2.388 meter per second. This is your du. So 2.388 divided by time is equal to du by dt. So from this one you have to actually calculate. This is your 0.798 meter. This is a meter per second. This is meter per second divided by second. That means meter per second square. Oh, so this is the acceleration. Now we know that, see, we have to, what is this value? This value we know, what is that, this value? 0.798 meter per second square. Multiply 1000, that means there is a negative. That means, what is it? dp by dx? That means dou p by dou x is equal to minus 10 to the power 3 into this velocity. What is the velocity? 0.798. So this is your 798 Pascal per meter minus. There is a minus. That means the pressure will change with respect to x is minus 79. So minus 798 Pascal per meter. 798 Pascal per meter. That means why this is negative? Why? Because why this is negative? Why? Because that means dou p over dou x is less than 0. This is called favorable pressure gradient. That means if x will increase, pressure will decrease. Yes, if x will increase, pressure will decrease. That means this is a high pressure and this is low pressure. So accordingly this you have to find such type of equation. Accordingly this you have to find this type of equation. No problem at all. Okay. Now these are the course portion we have to cover it. Other than you just go through that. You just go through that and revise yourself. Don't think very much. Don't think very much, beta. It is not a matter that you don't solve any problem right now. Okay. You cannot solve any problem. Just go through the revision. Okay. Just go through revise your formulas. Okay. Don't solve any single problem. I am requesting you. If you solve, if you want to solve, if it is that if you cannot solve that problem, you demotivated. So only go through that revision, revise your notes, revise your note. Don't see any formula numerical, revise your notes. That means formulas only, how to apply the formula, so that if you are stuck in the examination, if you have a formula, if you have knowledge about the formula, you can easily remove it. Okay, so go through that. Okay, so only you revise yourself. Okay beta, so best of luck Rama, Sonu, Krishna, all of you are okay. Okay, so there is a beta, we have planned that in night, in the evening after the second part, if the mechanical paper is finishes, so then we start the exam analysis at 6:30. Okay, we start the exam analysis at 6:30 sharp, at 6:30, so that we can you are all provided the questions, so that from the source we have to take questions. Many students are sit tomorrow. They are sit tomorrow in the GATE examination, and we solve at the after the 6:30. We solve all the questions related to the mechanical department. Okay. Okay. Yes. Yes, be there, be punctual, and at 6:30 we have start the sessions for the paper analysis of the GATE. Okay, GATE 23. Up to that, good luck and best of luck for the tomorrow exam. Thank you. Bye bye.